Okay, I think we'll get started. So we'll get back to our Lewis dot structures, and we'll look at a bit more advanced topics here, but this will help round out our ability to correctly assign Lewis structures for a whole range of molecules. Now, the first concept we need to talk about is electronegativity, and you ran into that when you were studying the periodic trends, although we haven't talked about it in the video series yet. Electronegativity is the ability for an element in a bonding pair to pull more of the electrons towards it. So if two elements are part of a bond and this is more electronegative than this, then the electron density will be sucked towards the more electronegative atom. Now, the electronegativity is just on some sort of empirical scale, and any book you're using will have a periodic table with the electronegativity values in it. And you should look at that, and what you'll notice is that electronegativity increases diagonally up like this. So fluorine is the most electronegative, and francium is the least electronegative. We don't really assign electronegativity to the noble gases because they're not really involved in any sort of mainstream reactions. So what does this have to do with the Lewis structures? Well, there's this concept of formal charge. And so as we fill an octet around each element, what we look for is there a charge deficiency or excess as compared to the natural electron density of the neutral atom, not molecule, not an ion, but the neutral atom. And so this is calculated via taking the group number, the group number from the periodic table, and using the A series, so 1A, 2A, 3A, then boron, and so on, minus the number of lone pair electrons, so we count each lone pair electron, and then 1/2 of the bonding pair electrons. So let's see how this works itself out in deciding a Lewis structure. So we'll start with this example of N, C, and S minus. So if you could check that there are 16 electrons here. So 5, 4, there's 9, 10, and then 6 from the sulfur. 16 electrons. So let's go through our algorithm. Well, we have to decide on a central atom, and here, maybe it's a little bit difficult. Probably not the nitrogen, but potentially the sulfur or potentially the carbon. So let's draw for both cases and see if we could figure out which is the best case. So we draw our skeleton structure. So single bonds and octets around everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So we have 4 too many. Means we have to have one triple bond or 2 double bonds. Okay, well, let's try that. So let's make a double bond here and a double bond here. Or we can make a triple bond. Or we would make a triple bond on the other side. Oops. And likewise over here. Okay, and now we want to assign formal charges to each of these to see how these formal charges are distributed. And once we do that, what we're looking for is the least amount of non-zero formal charge. So let's check the nitrogen here. So nitrogen is group 5, so we would go 5 minus 4 minus, so 5 minus 4 minus 6. So there's a -1 formal charge here. Carbon is group 4, and we have 2, 4, then 5, 6. So this is a -2 formal charge. And then let's look at sulfur. Sulfur is group 6, and there's 1, 2, 3, 4. So this is a +2 formal charge. And this is a very terrible formal charge situation because we have every element carries a formal charge, and 2 of the elements carry formal charges bigger than 1 in absolute value. Okay, well, let's try this next one. So here we have 1, 2, 3, 4, 5, so that's a formal charge of 0. Now we have a formal charge of -3 here and a +2 here still. So again, a very bad formal charge. This is even worse for 2 reasons. 3 is bigger than 2, and we have a negative charge on a less electronegative atom than nitrogen. So this is an even worse formal charge. Here, 2, 4, 6, 7. So this is a -2. This is a +2, and this is a -1 here. And so, again, a bad formal charge situation. So it's not looking good for sulfur in the middle. Let's try, let's try this one now. So similar case here, -1 on the nitrogen. Carbon, 1, 2, 3, 4, so that's 0. And sulfur, 0. So we see a -1. By the way, kind of as a check, the formal charge will always equal the overall charge. So if you have an overall negative, you're going to have something carrying a formal charge. All right, that's not too bad. Let's try this one. So this is a formal charge of 0. This is a formal charge of 0. And this is a formal charge of -1. Now we have the -1 on the sulfur. So we need to look up which is more electronegative, sulfur or nitrogen. Turns out nitrogen is. So of these 2 choices, this is the better choice because the negative formal charge is residing on the more electronegative atom. Here we've got a formal charge, oops, don't have enough electrons. Formal charge of -2, 0, and +1. And so that's definitely not a good formal charge situation. So we can cross out these. We can cross out this one. These are 2 pretty good Lewis structures. This one's best because the negative is on the most electronegative atom. All right, well, let's try some variants of this. So let's put C in the middle, but let's exchange out the S with the O. So let's compare these. So here we have these 2 same structures, but we've taken one from the same group, oxygen, and let's check this now. So this will be a -1, 0, and 0 formal charge. This will be a 0, 0, and -1 formal charge. And now this is the better choice because oxygen is more electronegative than nitrogen, and so here we do see not 2 double bonds, but we see a triple bond and a single bond as the best choice for the Lewis structure. We could try a couple of different ones. I think very clearly make nitrogen to phosphorus that's even less electronegative. So the appropriate structure there would be this one. And finally, the appropriate structure for this one, again, this will be more electronegative than that. And so these would be the appropriate structures for these choices. And so again here, formal charge is guiding us as to which structure is correct. Okay. So as you practice some more of the advanced Lewis structures, keep in mind the formal charge and really make sure you understand that and can put it into practice into a variety of structures. Now the next important topic we're going to talk about is resonance. And this is a little harder to understand but very critical. So let's imagine this polyatomic ion, the sulfate ion, SO4 2-. And so if we look at this, from the 4 oxygens, that's 24 electrons, 6 from the sulfur, that's 30, then a -2 from the overall charge, that's a -32 overall charge. So let's do our skeleton structure. And we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So it looks like we have achieved our Lewis structure. But now let's consider formal charge. This is group 6. So 2, 4, 6, 7. So it's a -1 formal charge, -1 formal charge, -1, -1, and -1. We should check the sulfur. Sulfur is 6. 4 around it, 1 from each bonding pair, so that's a +2. So this is a pretty bad formal charge situation. Now we might be stuck here if there's no other Lewis structures, but we do have this concept of hypervalency that can occur for row 3 or higher. So since this is a sulfur, we can go hypervalent with it and actually draw a structure where we reduce the formal charge. So it's a little different than the algorithm where we're taking away 2 lone pairs and creating 1 bond. Here we just slide a pair in as a bond. So let's do that. And we get something like this. Now we have a formal charge of 0 here, -1 here, -1, and 0 here. So that's a pretty good formal charge situation. We do have some carrying formal charge, but it's not a 2. It has to be an overall of 2. So we've gotten it down to 1, and it's on the most electronegative atom here, the oxygen. But there's even more to it than this. This has these oxygens are symmetric. So we certainly wouldn't expect that 2 of them are short and 2 of them are long. Short being the double bond. It's a little bit shorter bond, stronger bond, and then the weaker single bond. Well, that's probably, that doesn't work by symmetry. So this structure here is actually one of several what are called resonance structures that represent the actual structure of the molecule. And so how we have to do that is we have to consider putting a double bond in all of these possible pairs of positions. So let me redraw that. And how we denote that is we would go like this. and then we put a back and forth arrow. And we have another pair of double bonds. And we do this for all of them. So there's our third structure. We'll have a few more here. Okay, and let's see, it must be missing one more. Both down here, I think. Okay, so we have 6 different structures. They're all one structure representing the resonance structure. So this is our entirety. Now these are ions, so we should also, we can do it like this, I guess. Or you could put it on each of the individual ones. We have to denote we're carrying an overall -2 charge. Okay, so how do we interpret this? Well, is an actual bond a double bond or a single bond? What is the formal charge? And so on. So we have to think of this as an average. So here are 6 structures. Let's look at this oxygen right here. And since the oxygens are all symmetric, that's all we'll have to look at. Everything else will be the same. So in this case, we have 1, 2, 3 out of the 6 indicate a double bond. And 1, 2, 3 indicate a single bond. So we can represent that as a bond with a dash, where this is a 1.5 bond. Okay. And that will be the same for all the others. And so we can draw something like this to represent this whole thing. Now the trouble with this is it makes it hard to put the lone pairs on. So it's good to know this, good to know this. This is a good picture for showing the average of the bond, 1.5, and indicating that with a solid line and a dash line. And it's a good for indicating this spread of formal charge, because we can write that on there when we get to that. But we can't necessarily put, you know, is it this or is it this? We don't really do anything there. We just leave those off usually. Okay, well, let's do formal charge. So here, formal charge is 6 minus 2, 4, 6. So a formal charge of 0 there. And that would be the same here. But here we have a formal charge of -1, the same here. So half of the time it's a formal charge of 0, and half of the time it's a formal charge of 1. So this is a formal charge of -1/2. And same everywhere. And so we can see that we have improved the situation. We have, through resonance, gotten a formal charge down to less than 1, an absolute value of 1/2, which is good. And it's spread out over all of the electronegative atoms. And so this is what we call the resonance structure for this molecule. And again, we should include the overall charge. Okay. So resonance, when you can get resonance, that generally suggests a more stable Lewis structure. So if you can achieve a lower formal charge, the formal charge is on the more electronegative atoms, and you can get resonance, then you've likely achieved the most stable situation for that molecule, and that would be what you would present as the Lewis structure. All right, so this takes a lot of practice, and hopefully you've been practicing with some of the easier Lewis structures. Maybe you've gotten stuck on some of them, and now this will get you unstuck. So a good chance to practice a bunch now. So I would suggest pausing the way you go through the videos for just a minute until you get really comfortable with Lewis structures. I think if you want to do anything in chemistry at all, having a solid foundation in Lewis structures is just critically important. So take your time on it and get it down.